I'm going to go over a little bit of a derivation from something called the kinetic theory of gases. Now we're going to go over this in lecture, but I think those of you who watch this video, probably rewind a couple parts and rewatch, will feel much better during lecture, because it can be a tough topic when you first see it. And this is a derivation that we're going to do in lecture. So here's what's going to happen. First, let me give you a couple definitions. So we're going to look at the right-hand side. P is pressure. You're going to see I, momentum. So sometimes that's lowercase p in other textbooks, but here we're going to use momentum. That's mass times velocity. So U is velocity. You're also going to see collision frequency. So how often a gas hits or collides with, say, other gases or the wall of a container. That's equal to the velocity times n, the number of molecules, divided by v, the volume. So capital V volume, like in other chapters. So capital N is the number of molecules, which is lowercase n times, if you remember this, Avogadro's number, chapter 2. So lowercase n is moles now in the gas chapter. So moles times Avogadro's number, you'll see the moles will cancel. You're just left here with the number of molecules. Rate of velocity. Finally, kinetic energy, E sub k, is 1/2 mu squared. We also know that kinetic energy is proportional to temperature so far. And you'll also see something called EK with a squiggly on top. That means energy per mole. And we get that by multiplying Avogadro's number times kinetic energy. Alright, so I know there's a bunch of substitutions. Let's go over to the other side here. You see the derivation of what we're going to do with that. We're going to say that pressure is proportional to the momentum times the collision frequency. Hopefully that kind of makes sense. So the pressure is proportional to the momentum, how hard something's going to hit, how much momentum it carries. It's also proportional to the collision frequency. How many collisions per unit time it's having. The more collisions, the higher the pressure, and the harder the hit, the momentum, the higher the pressure. Thus, they're both directly proportional. The I is substituted as mu. The collision frequency is substituted in from these formulas on this side. I rearranged this, put n over v first, and the mu squared here on the right-hand side. Okay? Then we did this funny little math here where I multiply by 2, you see in blue here, and divide by 2. So that doesn't change the algebraic integrity of the equation, but it helps me out a little bit. Because now I have 2nv, and you probably now recognize 1/2 mu squared. That's just kinetic energy. Now really, you'll see in class we're going to deal with the average kinetic energy, but this will do for now. So I substitute from this kinetic energy. From here, because pressure is in 3 directions in, say, the Cartesian coordinate system, happens in the x, the y, and the z direction, we can actually turn this into an equal sign by putting a 1/3 there to account for all 3 directions. So really here, it's 2/3, the 2 and the 3, n over v, ek, but I substitute for the capital N. Remember, capital N is number of molecules. I substitute n times Na, or moles times Avogadro's number. And that's what you see here in blue. What that does is I'm actually going to bring Avogadro's number outside the parentheses. Go up here now. When you bring Avogadro's number out of the parentheses and look at these two things right here, that's EK squiggly, or really energy per mole. So if EK is just the energy, or kinetic energy, Avogadro's number times EK is the kinetic energy per mole, EK squiggly. Okay, now I'm going to rearrange this a little bit and bring the V, volume, and N, moles, to the other side. So we got PV over N equals 2/3 EK. And remember, EK, or kinetic energy, is proportional to temperature. So I'm going to put a proportional to temperature on the back end of this equation, meaning both sides are proportional to temperature. That has two results, actually. First, PV over N is proportional to temperature. So I wrote that down here. And I rewrote it, bringing the N to the right. PV is proportional to NT. You're going to see me work with this equation in class. It has a second result. The right-hand side is also proportional to temperature, or 2/3 EK squiggly is proportional to temperature. And I rearranged that to solve for EK. EK squiggly is proportional to 3/2 T. You're also going to see me work with that in class as well. So these are our two results. These are going to morph into two extremely helpful equations that we'll see in class. But I wanted to mainly go over the derivations and some of the substitutions and definitions that you'll see in class, because the first time you see it, maybe like right now, it's a bit confusing. But once you see it again in class, it'll make more sense really each time you see it.